have common multiple choice questions. This is video 2. We left off on the packet, page 12 in the packet. We just left off with this particular question. All right, so the next part we're talking about is independent, expected value, standard deviation, and transforming data. All right, in order for us to be able to add the standard deviations, I have to have X and Y has to be independent. If they're not, I'm unable to add or subtract the standard deviations. Of course, when I say subtract the standard deviations, remember standard deviation, X plus Y is equal to the variance. And so find the square root, and same thing with subtract, so I'm not, but that stays a plus sign. So that's the standard deviation, of course. Okay, so this one, first of all, asks us for the expected value. Expected value is just my mean, and it's asking, and then the standard deviation, of course, here. And this is wanting me, what this does is the players penalized 10 points for each minute the game is played and awarded 5 points here. So, and it says X is the number of cards and Y is the number of minutes. So I'm having 10 points is my deduction here, and then 5 points is my award here. So it's just going to be 5 times 9.5, if I read this correctly, minus 10 times 5.4 for the mean. That's simple. That's not a problem. And then for the standard deviation is what I'm doing is each one is I am going to be multiplying this by that number. So it's going to actually be 5 squared times 12.9 squared plus 10 squared times 1.1 squared, and the square root of that. And when you do the math, you end up with 65.4 and negative 6.5. A random variable is normally distributed with a mean of 5 and standard deviation of 25. And the random variable, there we go, is defined as this here. What's the mean and standard deviation of Y? Now, so this is X, right? This is X, and now Y, what have I done? I have added 2 and multiplied by 4. So what happens to the mean? The mean, I just take the mean as 5 times 4 plus 2. What happens to standard deviation? What happens here? Remember, I am going to ignore the plus 2. So I'm just going to 4. And that's it. Because remember, it's shifted. And it doesn't move as far as it doesn't add or subtract on the standard deviation. Okay, box plots. I'm going to run through these very quickly because they're pretty simple, but I just want to make sure I remind you what they all mean. Remember, this is the minimum. The next one is Q1. That's the median. Q3 and the maximum. Any dots you see on the outside would be considered the outliers. The fences that we get, remember, the formula is Q3 plus 1.5 IQR and Q1 minus 1.5 IQR. And remember, IQR is Q3 minus Q1. Now, the biggest thing I see is to remind yourself is that if there are, let's say 20 points on here, then 4 of them are here, 4 of them are here, or sorry, if I can divide, 5 of them are here, 5 of them are here, 5 of them are here, and 5 of them are here. Now these obviously are spread here. These are boom, 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 right, stacked on top of each other. In fact, they're probably the same points. These here are spread here, maybe here, and these are obviously much more spread out. So that's the biggest thing that I think people forget is they think that there's more data here because it's longer, but it's not that. It just means it's more spread out. Because remember, box plot is 25% in the first quarter, 25% in the second quarter, 25% in the third quarter, and of course 25% in the fourth quarter. So they're equal number of data points, just if more spread out or less spread out. All right, so it says in which of the following must be true. This is the key, must. The range of the number is greater than 90. Well, I go here, and that's going to be about 90, looks like by its tooth, but it's at 94. And here is 72. Well, clearly 94 minus 72 is not greater than 90. It says range, so that's not true. IQR of the number of arrivals is 22. IQR is Q3 minus Q1, so it's 80 minus 78, or 76 it looks like. So that's going to be 4, so that's clearly not right. The number of days had at least, the number of days that had at least 80 on-time arrivals, so I look 80 is right here, is greater than the number of days that had at most 76 on-time arrivals. The number of days that, well, we don't know. We just know that that 50% of the, or excuse me, this is 70, let me kind of erase all these so we can just see what's going on here. We know that 75% of our data lies underneath 80. We know that 25% of our data is under here, but it says the number of days that had at least 80, so that means from here to here, so that's 25%. And then this says is greater than the number of days that had at most 76%, or 76, which I guess I read it wrong initially, but that's 25%. So these here, this is 25% of the data, this is 25% of the data, so that's actually the same. So if I used the scenario where there's 20 points of data, there literally would be 4 in this area and 4 in this area. So that can't be right. The number of days that had from 76 to 80, so 76 to 80 is the center part, and the 76 to 80 is 50% of the data. So that's 50% of the data is equal to the number of days that had at most 76. At most 76, well, that's 25% of the data, so no, that would not be equal. The difference between the median and the lower quartile for the number of day on time is less than 2. So I look at median is here, and the lower quartile is here, which is, yeah, you can definitely see, if I erase it, you can definitely see it a lot better. But you see here, it looks like it's 1, and so that's the only one that's true. Let's just look at another one here. It says which one cannot be justified. So this one says the range of set 1 is equal to range of set 2. Well, that can be justified because you can see, look, they're identical. The range is identical. So that's not it, because look, we're looking for cannot. We're looking for the one that's wrong. The IQR of 1 is equal to the IQR of 2. Well, this is from 50, 35, so that's about 15. And this is about 45, 30, so that's about 15. So that's the same, so that's not it. The median of data set 1 is less than the median of data set 2. So we look at the median of data set 1 is here, and that's 35, and data set 2 is 45. Well, that's true, so that can't be it. Data set 1 and data set 2 have the same number of data points. That one, that's it. We have no idea how many data points they are. We just know the percentages. And then the same thing here. Okay, I'm just going to show you the answers here and let you do these on your own if you'd like. So this one here, the 2014, is E. I'll let you look at this one. You can pause the screen if you'd like. Do it on your own. This one here. If you have trouble with the questions, just let me know. Number 29, this one. Now, you're noticing there are quite a few box plots on here, so those should be some pretty easy points to be able to get. The main thing, again, is making sure that you're looking at the percentages, making sure you're understanding that it's a percentage and not a number. Okay, let's go ahead and identify the null and alternative hypothesis, and then what it is. So these are all for one prop. These two are one prop z-test. And you know that even by looking at the answer choices A, B, C, D, E. So we are asking for what's the hypothesis would be appropriate. So this is, let's go ahead and read this. A manufacturer of balloons claims that P, the proportion, so here's the claim. The proportion of its balloons that boost when inflated up to 12 diameter is no more than 0.05. So my claim is going to be P is equal. That's always my claim. P is equal. My ha is always P is either less than, greater than, or not equal to. And it says 0.05 right there. So I'm just going to go ahead and say it's not that one. It's not that one. Before I even read the question, I could see it's not that one. Okay, and then now I know that it has to either be these because they all have ho this way. Now I'm going to go ahead and read what read what I'm saying. It says that is no more than 0.05. So, but it says some customers have complained that the balloons are bursting more frequently. If the customers want to conduct an experiment to test the manufacturer's claim, so I'm going to test the claim. If I'm saying, what I'm saying is complain that they're bursting more frequently. So more frequently is going to be a greater than. So that's right here. Okay, let's read through this one here. A researcher is conducting a study of charitable donations by simply surveying the random sample of households in a certain city. The researcher wants to determine whether there's convincing statistical evidence that more than 50% of the households in the city give a charitable donation from last year. So that's what I'm trying to test. So that is going to be my ha. That's what I'm testing. Let's go through here, though, and I'm going to go ahead and, of course, which two can I cross out immediately? I can cross out these because, remember, my ho always has to be equal. And so I'm looking for ha that says more than 50%, so that's what I'm looking for right here. So A is the answer I'm looking for. An airline claims, before I even read this, let's go ahead and look at here and see. Remember, my ho is always, for the ones that we were just doing up here, ho is always for proportion P. For now, we're doing means, remember it's mu. So as soon as I look here, I can get rid of these three immediately. So it's always mu equals. So that could either be this one or this one. Now all I have to do is see what I'm claiming, I'm testing. And if I'm claiming less than, it would be D. If I'm claiming greater than, it would be E. So let's read through and see what I'm claiming. It says that greater than, you can read through it, and therefore it is E. Okay, for paired, remember what I'm trying to do. If I know it's paired, I know I'm looking for mu D. If I don't know it's paired, mu D equals 0 is what I'm looking for. If I don't know it's paired, if I think it might be two sample, it's going to be mu 1 equals mu D for ho. So, but if I do recognize it's paired, which let's go through and see, and when you see time before and after, most of the time when you see before or after, you know it's paired. Okay, so immediately I would say no, not these, because it's paired. And then I would look and I would try to see what exactly am I measuring. And I say, all right, well, it says, is there claim that the differences follow normal distribution, which is most appropriate to have the theory, and the theory is that it is actually an increase, that it's a increase in their performance. And so that would be that I'm saying that it actually makes a difference, because I'm asking for not a difference, but I'm asking if there's if their time gets better. So that's going to be greater than. Okay, so the next one here. So the first thing I'm going to do is I'm going to recognize what this is at first. From a random sample of 50 people, sitting pulse rates and standing pulse rates were measured from each person. So when I'm seeing sitting and standing from each person, immediately I'm saying it is definitely going to be a paired. I'm seeing sitting and standing, and it's from each person. So I'm noticing I have two treatments on one person, so I know it's going to be paired. And then I continue to go for, and I see which of the following is appropriate test to determine if there is a difference. Whenever I say there's a difference, that means the ha is not equal to, because I'm not asking if it's greater than or less than, so that's why I'm going to settle with D. %95 confidence interval. All right, these here are a lot of reading of kind of trying to figure out what's what and what's not what. So this is saying which is the best interpretation of this. Whenever you see 5% of the time or something like that, that usually is not the answer. I've sometimes seen when it says a percentage-wise, but this one is not. It's saying this 5% of the time for responses is less than here. And it's also the way this is worded, this is too deterministic. This is saying this is actually happening here. Whenever you see probability, that's another key that it's not going to be it. That's not the correct one. Again, 95% of the time, because this is too deterministic. This is telling me this is happening 95% of the time. And that's not what it's saying. We're saying we are 95% confident that the mean time, that remember, I'm saying that the true mean time is contained in there. Remember, this is created from my sample. These guys are my sample. And so I'm saying that the true mean is contained in the interval. So you can know that's either going to be D or E. So let's look at the difference says. We are 95% confident that the mean time for the responses is in the interval. That looks good. Let's look at the difference of why E was wrong. We are 95% confident that the randomly selected time, C, no, that would be that the population, which is what we have in the one before. And that's what makes D correct. Okay, let's look and see the interpretation of 95% confidence interval. Now, I haven't even read the question, but I'm going to tell you we can go through these and we can see why this would be correct or incorrect with some of these answers. With a 100 confidence interval, we can be 95% confident that the sample proportion of citizens of the United States who are optimistic is correct. Okay, so for one, is correct is really deterministic. Secondly, I'm not looking for my sample portion. What I'm trying to do, remember, I'm trying to do all. I'm looking for all the citizens, and I'm looking for the population. Remember, my confidence interval, how do you create a confidence interval? Well, let's kind of remind ourselves. It's P hat plus or minus Z star P hat Q hat over N. And why does P wear a hat? Because it's a stat. And same thing when we do X bar. X bar is my sample mean. It's when I ask 100 people, it's my actual data. But what I'm saying is when we create this, we end up getting a confidence interval that comes from my sample. This is from my sample. And I'm asking, is my population in my sample? So that's what we need to be looking for, all the population in the sample. Let's read, I'm going to read, B's the answer, but let's read the other ones of why they're bad. So let's go to C next. We would expect about 5 out of 100 confidence interval to not contain the sample portion of citizens. All right, of the United States who are optimistic about the economy. All right, now look, again, I am looking for all the citizens, not the sample. Of the 100 confidence intervals, 95 of the intervals will be. That is too deterministic. We cannot say it will be. We're only 95% confident, but we cannot say that 100% will happen. And then when it talks about probability, remember, confidence interval is not a probability. It is either in the interval or it is not in the interval. And so when it talks about it as a probability, that is not correct. So let's look at the correct answer. We would expect about 95 of 100 confidence intervals to contain the true proportion. That's it, of all of them. Okay, and see, we're expecting, so we're not being deterministic. Let's do this confidence interval now. Go ahead and try it by yourself, and then take the video off pause. All right, so this one says probability. Remember, it's not a probability. Confidence interval is not a probability, so you can cross that one out. The answer is B again, so let's jump to the other ones and see why they're wrong. So this one, you see, of random samples of the same size will result in a confidence interval that includes the proportion of all adults in the sample Remember, it's in the population. Approximately 95%, I'm reading this one now, of all random samples living in adults will indicate. And so that's another problem, is that I don't know if it will indicate this, because that's too deterministic. And then, of course, I'm trying to have, I'm trying to be confident, but not dogmatic, and I can't just be, I can't just say it exactly like that. And finally, E says approximately 95%. I'll read the rest to you. You run out of, it doesn't have it all on there. Of all random samples living in the United States will result in a sample proportion of 0.66 adults who are satisfied with their health plan. And it says a couple issues. One issue here is that it's a sample proportion. Another one that it's too deterministic. So read this one and see why it's good. Approximately 95% of random samples of the same size, that's good. From the population, that's good. will result in a confidence interval that includes a proportion of all adults satisfied in their health care plan. That's what. And notice it's approximately, so it's not too deterministic. All right, let's talk about conclusion from p-value. So we've talked about p-value in our other video of what p-value means. And p-value, when p is low, so it's less than alpha, we're going to reject ho, and we're going to state ha. We're going to say, yes, we have enough evidence for ha, but never prove. All right, so this one says the consulting statistician reported the result from a learning experiment to a psychologist. The report stated on one particular phase of the experiment, a statistical test resulted yield in a p-value of 0.24. So in my mind right away, I'm saying p-value is equal to 0.24, which is greater than any reasonable alpha. So that's going to be a fail to reject. So, which fail to reject means not statistically significant. So it says was statistically significant, and no, was not. So I need to get to the was not. So it's got to be C, D, or E. So then I look here, it says the test was not significant because 2 times this is less than 0.5. No, that's saying if it's two-sided, it's just confusing things. D says the test was not statistically significant because if the null hypothesis were true, one could expect to get a test statistic at least extreme 24% of the time. Guys, this actually is the definition of p-value, exact definition of p-value, that this is the p-value is the percentage of time this could happen by chance. So obviously we're saying 24% of the time is really not that low for it to happen by chance, so it's not statistically significant. All right, number 17. So for this question, it asks, assuming the conditions for inference were met, is there sufficient evidence to conclude with a p-value I have of 0.283? Well, obviously the p-value is way greater than that alpha, so we're going to say fail to reject, and we're going to say not statistically significant, because this is greater than 0.05, which is E. This question, the p-value for the test was 0.08, and I'm using alpha here, so of course p-value is equal to 0.08. That's greater than 0.05, and I'm going to tell you that says fail to reject, and that's not statistically significant. Because if it's statistically significant, I'm changing over to ha, where I'm saying, yes, it's statistically significant to state something new, to state ha. So if you read through that, is C is the answer. The other ones just don't correspond. A survey was administered to parents. We're naming the type of sample here. So let's remind ourselves real quick, I guess, is that we have stratified. And stratified is when I have like freshmen, sophomores, juniors, seniors, and then I'm going to take a simple random sample of each one. So I would take maybe 3 juniors, 3 seniors, 3 freshmen, but I'm putting them all in separate strata. And then if I took 3 of each, then these 3 people of each one, which all 12 of them would be my sample. Now let's look at what cluster is. Cluster is if I have it's the cake one where I have lots of layers of the cake, but each slice of cake looks identical. And so basically each of your slices, let's call classrooms. In mine, I say we have Coach Myers, Mr. Fowler, Mr. Paul, Miss Cummings. There's mine, and then Miss Torres. Okay, so we have all these different classrooms in the math department, and each of them look really similar, and I'm going to randomly select, let's say, 2 of them. Let's say I chose Miss Cummings and Coach Myers. And all of the students in the classroom get surveyed. But the cluster, the whole point is each classroom, if you walk into any math classroom, it looks pretty typical. They look really similar. You've got a similar makeup of the population. I've got systematic random sample where you have 1, 2, 3, 4, 5, let's 6, 7, 8, 9, 10. And then I randomly, let's go maybe up. You have a random start, and then you're going to go up maybe every 2 people after that. That's systematic. And then convenient sample is just when you're sampling whatever's convenient, whatever's close, whatever's easy for you. And of course that creates bias, and that's not any good for you to do. I believe, and then SRS is just a random sample. If I have, like you guys sitting at your desk every day, when I say, okay, I'm going to do an SRS and I'm going to choose desk 1, desk 6, desk 3, and that's the only one, SRS is the only one that everybody has an equal opportunity of being chosen, and each group has an equal opportunity of being chosen as well. To number 15 here. For identifying the type of sample, so just kind of talk through the different types of sample. We didn't actually, I guess I didn't finish this one on number 9, so let's finish number 9. So it says, a survey administered to parents of high school students in a certain stage to see if parents thought academic needs were being met. To test, select the sample, the parents were divided. So when I'm saying divided, I know it's not going to be SRS, so it's not going to be systematic. It's not going to be cluster, because they're just in 2 groups, and we are taking a group of 100,000 here, a group of 100 here, and then a random sample of 100 parents, so that's SRS. So that definitely described strata for us. Okay, this one as well. A high school student statistics class wants to conduct a survey to determine what percentage of students would be willing to pay a fee. So the first thing it says, 20 students are randomly selected from each, and it gives me the stratas. And so again, that is strata. I noticed a lot of stratas in here. So just keep that in mind. I'm not saying strata is the right answer all the time, but just keep that in mind. If strata comes up often, kind of that's what seems like what this particular question is gravitating towards. So you may, when in doubt, choose strata. All right, so for 2015, this one here, the researcher has 20 public schools and 20 private schools, and it says that it wants to do an SRS of both. Again, we are at strata again. Okay, observational study versus experiment. The biggest thing you're going to want to look for is experiment has a treatment. Okay, and observational study does not have it might say randomized treatment, but it doesn't matter. It says does not have a randomized treatment. Doesn't matter, doesn't have randomized treatment or any treatment. So sometimes it says that. So just be careful there. Like this one here, this is the answer. In an observational study, they are not randomly assigned. Treatments are not randomly assigned. That's right, because there's no treatment. So that's a true statement. So be careful on that, because I know that tricks people up, because they say, well, they're not randomly assigned. There is no treatment. Right, there's no treatment. So that's a true statement. Whereas a randomized experiment, they are assigned randomly. So this one here, which of the following is a key distinction between well-designed experiment and observational study? And of course, we're looking for treatment. And with treatment, what can I do with treatment is that I can do cause and effect. So when I have treatment and I do randomized treatment, I can do cause and effect. So remember, random assignment of treatment allows me to do cause and effect. With observational, I can just do like a correlation or association. I can say this seems to associate with this, but I cannot do cause and effect. All right, so this one is asking for generalization. What conclusion is not appropriate? If I read through the problem, I'm going to notice that the issue, it says, first of all, this is observational. No, these were not observational. This was actually an experiment. You look at it, they're manipulating it. And it did it says it didn't do into blocks by a variety of means. It says which is conclusion is not appropriate. Why is it not appropriate? That has nothing to do with it. It's that the problem is the experiment is all about green beans, right? But look at his conclusion. The scientists found that the mean weight of seedlings in the group of the new fertilizer was significantly greater than the mean of the weights. The scientists concluded, here's his conclusion, that the new fertilizer was more effective than the others for all vegetables, and that's the key there. The problem is he didn't use all vegetables in his experiment, and so you just got to really watch those reading there. All right, so this one is going to be a difference here. What type of study was conducted and what response variable? So the first thing we're going to do is we're going to see, is this an experiment or is it an observational study? It says measurements were taken. Now, I didn't manipulate anything. So when I look here and I keep reading, it says concentrations were taken, 9 measurements here, 9 measurements here. So immediately I know it's definitely not an experiment. A census means they're doing the entire everything, so that doesn't even make any sense. I know you can't read E. A says an observational study was conducted and the response variable is the concentration of chemicals, and which is what I'm measuring. I'm measuring it, and what am I measuring for? I'm asking to see how much concentration of chemicals is exactly what I'm looking for. E said an observational study was conducted and the response variable is the depth of water. And it definitely is not the depth of water. That is going to be the level of my study of where I am measuring. So, but the response variable is the concentration, what I'm measuring. A florist wanted to investigate whether new powder added to the water to cut flowers had kept flowers fresh longer than just water alone. For a shipment of roses that was delivered to the store, the florist flipped a coin before placing the rose on the individual container with the water. If the coin lands on heads, the rose was placed in the new powder. Otherwise, it was left alone, the water alone. Which of the following is the description method used by the florist? All right, so census, it says everything. That doesn't really make any sense. It's definitely not an observational study. But the way I did this is if I had roses, and this would be random assignment. And of course, this would be group 1, and group 1 got the treatment, and group 2 got the placebo, or the water, right? And so what does this look like? I didn't put them. Block would be if I put them in maybe a group of red roses and white roses, and it wasn't that. Match pair would be the same thing, except maybe I would match 2 roses that seemed similar and had a similar thing, or did the same treatment to the same rose. So this is a completely randomized design of what I described. Okay, describe sampling distribution. So let's remind sampling distribution. For the mean of a sampling distribution, remember, equals the mean, the population, and the standard deviation is going to equal PQ over N. Sorry, I was going to put PQ hat over N. There we go, PQ over N. So, and then for means, which I'm going to go down here in a bit of, and so that's, and remember, when both NP and NQ, when we both have that conditions, when we have NP and Q, that's going to be approximately normal. All right, so those are the different things that we need to look for. And it doesn't matter, this is the thing, is it doesn't matter how many what the shape of the population is. If the population is skewed to the right, the sampling distribution is going to be normal if my normal conditions have been met. All right, so I'm going to look here, and you're going to see when the first thing I'm looking at, it says that I have the mean of 10 and the standard deviation of 4. Okay, now it says a random sample of 64, so that's important because I'm going to do, of course, my mean is going to be 10, so this all says 10. But my standard deviation is going to be Now this is, I did the sampling distribution, so I didn't see it sampling mean, so that would have been for proportion, but for means is going to be also mu, and then standard deviation is going to be, over square root of n. So we're going to use 4 divided by 64, square root of 64, which is obviously 4 divided by 8, which is 0.5. So that's this one and this one. So now we have to look at what's the difference. So we know it's not these here. Now it says this is skewed to the right. Well, some people may say skewed to the right because it says that is the population skewed to the right. However, because now with sample, this is of course with proportion, but with n greater than 30, with means, that's what's going to be. N is going to be greater than 30. Then it's going to be by the central limit theorem, it's going to be approximately normal. So those are the reasons that I know that it's normal with a mean of 10, standard deviation of 0.5. So let me go over those one more time because I was thinking that we were doing a population one, but we did the mean ones. So remember, if it's population, it's p hat, and if it's mean, it's x bar. And for sampling distribution, the mean of p hat is equal to the proportion. For means, it's going to be x bar is equal to the mean. So the mean doesn't change, but the standard deviation is going to equal PQ over N. And for the standard deviation for here, of course, it's going to be sigma over square root of N. We're looking for NP, NQ greater than 10 to be a normal distribution if it's proportion. We're looking for N greater than 30, greater than or equal to 30, to be, by the central limit theorem, to be a normal distribution if it's means. Okay, so the same thing here we're going to look at the mean length is 5.5, so these should be 5.5, and they're all 5.5. Okay, now it's the standard deviation of 2.6, but it says they stayed for more days and a random sample of 100. And so if I look at 2.6, I know that's definitely not going to be correct. So 2.6 is not correct because I'm looking for 2.6 divided by square root of 100, which is 2.6 divided by 100, or 10, which is 0.26. So that's 0.26 and that's 0.26. So let's see the difference. So we know it's obviously not this one. This one says strongly skewed to the right. This one says approximately normal. How big is my size? N is 100. That's greater than 30. So therefore, that's going to be normal. All right, this is reminding you how to use normal CDF under the curve, finding the percentage under the curve. So you're going to, this is the weights of a female cross-country runners, approximately normal, with a mean of 122 and a standard deviation of 8. What's the following closest percentage who weighs between 114 and 138 pounds? And so this is just a normal CDF on your calculator. How do you get there? Menu, stats, distribution, normal CDF. And you have the mean is 122, the standard deviation is 8, the lower bound is 114, and the upper bound is 138. And when you get that, you will get 0.82, and that's going to be your answer. Okay, this one here, it says approximately normal. Population of 10,000, a mean of 10, standard deviation of 0.2. So mean is 10, standard deviation is 0.2, which of the following is the shortest interval that has approximately 4,000 shellfish. All right, so I'm going to go ahead and look here, and it says the mean is 10 here, and the standard deviation is 0.2. And I want 4,000 shellfish, so 4,000 I'm going to say out of the 10,000 is I want where it's about 40%. So I'm just going to say, I'm going to look at this, and you can go through and do every single one of this like this. If you're not sure how to do it, here's an alternative way. Normal CDF, the way we just talked about, mean, 10, standard deviation. All of these, you could try lower bound, upper bound. You could try each one and see which was going to get you 40%. Okay, you could do it that way. Or you can kind of look at our rule of 68, 95, 997. You can say, look, I'm going to go here, and I know that this is going to be 9.8 to 10.2, and you can keep going forth and keep going on. But you can kind of look at each one from this one. Let's look at start here from 0 to 9.9. So that's basically from here to here, which obviously is way more than 40%, because you can see that it almost hits at 10, and obviously this here is 50%. So you know it's probably not that one. You could go here at the next one, 9.7 to 10. 9.7 to 10 is going to be, let's kind of look at, see where that's going to be. That's going to be 9.7. Remember, this goes to 9.6. So 9.7 is halfway here to 10, which clearly that's going to be, of course, 68% in the middle. So that's 34% there. And then it's this aspect here, and so it's a little extra, so that doesn't seem like it's going to fit. Anyway, you can keep going on, and if you do the math and you can kind of go through it on each one of this is lower bound, this is upper bound, then if you're not sure which one, it ends up being D. And so I'll go ahead and put them in for you just so you can see it. So menu, stats, distribution, normal CDF, lower bound, 9 point, I'm looking at D, 895, upper bound 10.1005. The mean for this was 10, and the standard deviation for this was 0.2. And there's 40%. Again, you can do any of the other ones, and you're going to see that you don't get 40%. And so that's the easiest way to do it, probably. A caffeine count of 8 ounces of a certain cola drink is approximately normal with a mean 33 and a standard deviation of 1.2. Approximately what percent of the cans cola have a content greater than 35? So the area, so I'm looking for what percent is greater than 35. So my lower bound is going to be 35 and my upper bound is going to be infinity, 9999. I'm looking for this. And again, it's normal CDF. The distribution of monthly rent is approximately normal, mean, standard deviation. Graduate student looking for a 1-bedroom wants to pay no more than 800. Of the following, what's the best estimate of the percent that's going to be a 1-bedroom rent at most 800? So I'm looking for at most 800. So 936, I'm looking for 800 to be my upper bound, and my lower bound to be negative infinity, or negative 9999. And that indeed is able to get us 1.3%. At a certain store, the distribution of weights of the carton of large eggs approximately normal with a mean of 26. And based on the distribution, what's the following interval that could be the greatest proportion of cartons of the eggs at the store? So it didn't give me a standard deviation, but that's okay. So it's saying a mean of 26. And so which one is going to be the biggest one? So I'm just going to, since these are by twos, this is not necessarily a standard deviation, but I'm just going to make it as if this is a standard deviation just so you can kind of see, because I'm looking, I'm like the largest one and the answer is 32, the smallest is 20. So this will contain most of what I'm trying to do, looks like. So then I can see, oh, well, if this was kind of what the distribution would be, 20 to 24 would be here. I'd say, okay, well, the next one, 22 to 26 would be here. You see, that's bigger area because it's in a bigger space. 24 to 28, that's even more because it's smack dab in the middle. And then it continues. 26 to 30 is going to be the same as 22 to 26. Like this here is the same as this one here. It's the same area. And the same thing, 28 to 32 is the same as the first area. Those two are the same. You can see the middle area, though, is where the most of the area is And so therefore it's going to be a, and it doesn't matter what the standard deviation was. It could be 10, it could be 20, it could be 0.1. It doesn't matter. But this here is going to be the most area because the mean is centered right in the center, and that's where most of the area of the normal model is. All right, so this here is the formula for confidence interval for means. If you look at your formula chart, the formula chart will say statistic plus or minus critical value times standard error. And if you look at the back, it'll give you the formula for standard error. You look at your calculator cheat sheet that I made you, and you'll also see the formula on the confidence intervals. And this is a one sample mean, so you can look at those as well. So this one looks like I'm going to find, I mean, just looking at this, its means are all the same. The only thing is if I said the results can't be sampled, the sample's too small. If I looked at that, and the sample size, is 11, right? I believe 11 is the sample size. So that doesn't make a difference. It's of course if it's unimodal or symmetric or outliers or things like that. So we know that's not right. So I look at the difference here. They're all 301, they're all 301, they're all 301. But the bottom, this is 11 and this is 10. Well, we know that it's going to be x bar plus or minus my critical value, which is the t star, times sigma over square root of n. So I'm looking for n. N is 11. So we know it's definitely not these two down here. So the biggest difference is trying to find my t star. My t star is either 2.228 or 2.201. In order to find t star, of course, we're going to be using inverse t. And it tells me that I'm looking for a 95%. So 95%, the area, remember, I'm the center 95%, so I got to include the tail, and that's where the 0.975 comes from. The degrees of freedom is n minus 1, so that's going to be 10. Once I put that into my calculator of inverse t, which is the same menu that we've been on, menu, stats, distributions, inverse t, then you are going to get 2.228. All right, for confidence interval, this one here is a proportion. So I'm kind of looking through here. I see all of these are the same. Now the thing is for proportion, remember, the thing is that you want to do is I don't even have to read this because I know that's what I'm looking for. I'm looking for a 99% proportion, right? So I'm just going to look at these and say, okay, let's kind of see which ones can be. So the first thing is this first number here, we need that to be in my interval because what I'm looking for is P1 hat minus P2 hat plus or minus Z star. And then we have P1 hat, Q1 hat over my P pooled. Or N1 plus P2 hat over Q2 hat over N2. So yeah, we're not going to be using my P pooled because that's in a test. This isn't an interval. So I'm just going to be kind of matching. Do I have this and this? Now, where would I get this? You can get this on your calculator cheat sheet. Of course, you can look and see what it is and recognize that this is a 2-prop interval. And you can say, okay, well, then that's where I'm starting to match. This matches. I'm matching up. And I look at these, and these don't match up. So these look like they're pooled at the bottom, so it's not those. And then I look at the other one, and I'm trying to match this one up. And I say, okay, 0.058. That matches up. Oh, they're all matching up nicely for me, okay? And I look and I see, okay, well, obviously all of those are exactly the same. So the only difference is going to be this part here. Is it 1.96? Is it 2.326 or 2.567? 2.576, sorry. All right, so it says 99% confidence interval. Well, 99% confidence interval, if you don't have it by memory, you can inverse norm. And your area is going to be, of course, that 99% plus the tail. And, of course, the mean is 0 and the standard deviation is 1. And if you go ahead and do that, you actually do get the 2.576. So on this one, honestly, the only thing that you really needed to know is that the Z star. So when I read this, I recognize this as a proportion. I can look and I can see it's all the proportion. And the first thing I'm going to make sure I do is I look and I see, okay, I have 15 out of, my p hat is going to be 15 out of 500, which is 0.03. So I look and I say it's not this one, not this one. Okay, that's where I'm beginning. I look also and I see that this is just talking about a one prop z-test, so it can't be this one. So I look and they're obviously identical. The only difference is my z-star again, and I'm looking for 99%. Well, I just did the 99% on the last problem, but I would do inverse norm. The area, of course, would be what we just talked about, 0.995. And of course, you get C again. For the confidence interval for means, for a one sample means, same thing is that, remember, we have x bar plus or minus t star sigma over square root of n. So really I'm just kind of looking for the differences. So I don't even really have to know the means. I'm looking for the standard deviations. You can see obviously it can't be this one. Just looking at it, it's in completely the wrong form. Now wait a minute, I stated that. I should have said, well, I know this is 1.5 before that's my standard deviation, so 1.5 has to be at the top right there. And when it makes sense, this one here might be correct. Because if, for instance, if n is 9, which I think it is, yes, n is 9, yes. The square root of 9, you could also write it, I could write it like this, 1.5 over square root of 9, or of course I could write 1.5 over 3. So I was just doing it based on what the formula is, but be careful because obviously it could be that. So I look here and it can't be this, so it can be one of those two. So the main thing, again, that I'm looking for is inverse norm. So that's something you guys need to make sure, or inverse t, sorry. You need to make sure you do, and it's looking for a percentage, 95%. Now be careful. It's inverse t, 95%. We do 1.96 all the time, but that's for a z-star. For t-star, it's not that way. Area, 0.975. And degrees of freedom, remember, is n minus 1, so that's 8. But you can bet when it's inverse t, and I have a lower degrees of freedom, it was not going to be 1.96. They're trying to trick you. So it is actually 2.306. Trying to be tricked. All right, I'm recognizing this as a one prop z interval. And again, I'm going to look and I'm trying to see, I have 180 out of 300, so that's my p hat. So 180 out of 300, and I look and that they have it in decimal. I do the decimal, and that's 0.6, so I know it's not those. The other thing I'm going to look, well, these are all, these match, so I don't really have to look at that. And the only difference, again, comes down to my z-star. So the z-star is 98%. So notice a lot of them aren't the nice little 1.96 that we do. So inverse norm, and the area is going to be 0.99. And the mean is 0 and the standard deviation is 1. Okay? And then, of course, that comes out to be 2.33. Linear regression chart. All right, I saw a lot of you guys miss these things here. So let's talk about the linear regression chart and what this is. Okay, so first of all, before I even read this problems, let's just kind of talk through these things. So here is, if I ask you to write my regression equation. Here's my regression equation. Is this going to be right here? Okay, and the way I like to write it is this. I go this plus this times this. And that's literally going to be it. And I say, okay, so printing time hat equals 11.65559 plus 3.47812 times size. And that's my regression equation. All right, next things, notable things. This is talking about the constant, the y-intercept, and this is talking about the slope. But guys, we have not done anything on regression on the y-intercept, so we are not going to be using this data here at all. We've been doing a regression based on the slope. This here is the standard error of the slope, and if you do, and this here is this, and this here, of course, is my slope, and if and this here is the t-ratio. Remember, the t-ratio is like, remember when we do, we have my, in order for my slope, I have my slope divided by standard error. Well, let's put this in. Well, the t, that's going to be 3.4 0.7812 divided by 0.294 equals 11.8. And remember what that means? That's this here. It goes here. All right, so you notice that 3.47812 divided by 0.294 equals 11.8, and that's my t ratio. And all that means is that's 11.8 standard deviations away from the mean, really with a really tiny p-value. It's basically 0, and that's what the p-value is right there. All right, so when you are doing, remember for my confidence interval is my slope, my beta, which I've had, that's my beta, plus or minus my critical value. My critical value is t star, degrees of freedom's n minus 2 for regression because you have an x and a y, so I've got two variables, that's why it's n minus 2. And then it's times my standard error. And it's given to you right here. So it's just 3.47812 is my slope, plus or minus my critical value, which I am going to have to do my critical value at 95%. So I'll just kind of put that there, t star 95%. So I'm doing t degrees of freedom of, let's see, it tells me right here, 20 degrees of freedom for 95%. And then times my standard error, which is just right here, 0.294. So you got to see that I want you to see that here, this here is my confidence interval right there. That's it. That's my confidence interval. Of course, you have to calculate the critical value, but we have done that before, and you will see that obviously it can't be this, can't be this. Just looking at these different numbers, 0.294 can't be this, so it has to either be A or C, and then when I put in 0.975 for my area for degrees of freedom of 20, I do indeed get letter A. All right, same thing here. Let's go ahead and find your confidence interval. For 98%, it's going to be right down here. Now on this one, if you notice, there's no t score and no p-value, right? Well, the way you would get it, if I had to find it, would be 1.161 divided by this would get you your t. And then you could do a t-CDF to be able to get your p-value if you needed it. I don't need it. That's just food for thought because sometimes you will need it. Not on this problem, I don't need it. So I'm looking for 0.161, so we know it's not this one, and 0.073, so it's one of these, and I have to determine which t-star. So t-star for, it says 22 observations, so that's degrees of freedom of 20. Guys, I guarantee you, if you they're going to have a degrees of freedom wrong in here. They'll have 21 to kind of trick you because of not remembering that it's n minus 2 because it is a degree of freedom of n minus 2 because it's a linear regression and I have an x and a y. So I do end up getting 2.528, which is C. Confidence interval again, let's look here. Right here, there's your confidence interval. So it's this plus or minus the t-star degrees of freedom, my degrees of freedom. I look and I see how many. I have 23, so the degrees of freedom is 21. All right, so again, you look it up, and you have, and it ends up being 2.08. So you can see, do not fall for dividing it by square root of n because it's already, standard error means I have already divided by the square root of n. That's standard error. That's what I've already done, the standard deviation. That's what standard error is. Z-score formula, remembering the Z-score formula, the Z-score is going to be my observed minus mean divided by the standard deviation. All right, so, but remember, this is a little bit trickier because it says approximately normal with a mean of 78, standard deviation of 8.6. And I want to know what z-score can I have, which for 33%, which 33% above the scores. So I'm looking for this here where 33%, basically what I need to do is find my z-score for that value right there, which that means this is 0.67 because all of these are z-score formulas. So I can tell you what it's not, definitely. It's not going to be these because it's going to be, when it says 33%, it's not going to be coincidental that the z-score and the percentage is the same. So how do you find that z-score? Of course, you can go to inverse norm. and the area is 0.67, the mean is 0, and standard deviation is 1, and you're going to find that z-score here is 0.44. You can even look at this, and obviously it can't be this top one because that's definitely not a z-score formula, so it has to be this one. But the reason 0.44 lies where? 0, 1, 2, right here, 4, 4. And this area is 33%. Hanging in a large city is 65% in favor of increasing taxes to support the public school and 35% against such increase. If a random sample of 500, what's the probability that more than 200 of the people will be against the taxes? So I need to see what's this probability here. All right, to be able to see what this probability is, it says more than 200. Well, let's just do this the way we would do this with, this is going to be, if it's a z-score, observed minus mean divided by standard deviation. So that's just going to be the z-score is, it says 200 of the 500, 200 of the 500, minus, what was it, the percent that it says, 35%, divided by the standard deviation, which is going to be this, of course, 0.35, 0.65 over 500. So that indeed is E, what it's measuring. Let's talk about why it's not A and why it's not B. These are binomial. This would sound like what's the probability that 200 of the 500 people in any room believe 65% versus 30% using the against or for, and this would be the opposite of that. But this would be, given that there's 500, what's the probability that 200, any 200 are there? But this one here is specifically against here. This is just some sort of combination where I'm asking for all the different combinations of the 200 people. This is just asking for the exact probability. All right, you have to know how to make sure you know how to do the expected value. And remember, to do that, if I'm acting for the expected value or the mean, remember it's 1 times 0, this times this one, plus this one times this one, plus this one times this one, plus this one times this one. This one asks, so that's how you do expected value. Let's see what this says. The faces of a 4-sided fair dice are numbered 1 through 4. For a certain game, just erase this. For a certain game, the die is tossed and the number lands face down as recorded. The table below summarizes the points for someone that earns the number of points. So if they roll a 1, they get no points. They roll a 2, they get 1 point. Roll a 3, no points. And roll a 4, they get 2 points. Consider 2 independent tosses. So they're doing this 2 times. Let the random variable s represents the sum of the points earned from the 2 tosses. What's the probability of the distribution s? Well, obviously we know the probability of all of these is 1/4, 1/4, 1/4 originally, correct? But now let's say what happens if I roll it twice. So if I roll it twice, this is how you could kind of do this. Is I do 1, 2, 3, 4, 1, 2, 3, 4. And if I roll a 1 and then a 1, that would be 0 plus 0. If I roll a 1 and a 2, because I'm just doing the 0 plus 0 there. If I roll a 1, I get a 0. If I roll a 2, I get a 1, so that's 1 point. So this one's just, if I roll a 1, that's a 0, obviously, and a 3, that's a 0, and then a 1, that's a 0, and a 4, that's a 2. So if I roll a 1 and a 2, that's a 1. If I roll a 2 and a 2, that'd be 1 plus 1 is 2. If I roll a 2 and a 3 is 1 and 0. A 2 and a 4 is 1 and 2 is 3. Then I would keep going and I'd say, okay, a 1 and a 3. A 1 and a 3 is 0. A 3 and a 2 is 1. A 3 and a 3 is 0. And then a 3 and a 4 is 2. A 4 and a 1 is 2. A 4 and a 2 is 2 plus 1 is 3. A 4 and a 3 is 2. And finally, a 4 and a 4 is 2 plus 2 is 4. So now I would say, okay, so I have 4 zeros. And so in order to be able to 0, I have 1, 2, 3, 4 times 1, 2, 3, 4 possibilities. So that's 16, possibilities. So a 4 out of 16, or 1/4, obviously, 0.25. If I were to put it in decimals, because that's what it looks like it is. A 1, the probability of getting a 1 is going to be 1, 2, 3, 4. So a probability of getting a 1 is also 0.25. The probability of getting a 2 is going to be 1, 2, 3, 4, 5. So 5 out of 16. The probability of getting a 3 is going to be 1, 2 out of 16, or 1/8. And the probability to get a 4 obviously is the 1 out of 16. So when you go ahead and do the math, you can see that D is the only one that works, 0.25, 0.25, 5 out of 16 is 0.3215, 2 out of 16 is 1/8, or 0.125, and 1 out of 16 is 0.0625. So that's how you would do that problem. Expected value, again, as I said, you're going to multiply these. And then that's going to get your expected value. And that tells you the number of sweatshirts you're going to buy. And then each sweatshirt sells for $25. So what's the total expected value of the sweatshirts? So you'll take the expected value and then you're going to multiply it by $25. So you're going to put this into your calculator. So let's go ahead and put it into our calculator. Let's get my CAS here. And you have 0 times 0.3, which is 0, so I'm going to leave that. 1 times 0.2 plus 2 times 0.3 plus 3 times 0.1 plus 4 times 0.08 plus 5 times 0.02. And that's my expected value, so that's 1.52. And then I'm going to multiply it by $25, so because that's telling me I'm expecting to get 1.52 t-shirts. $25 is $38, and that's where I get $38 from. All right, this is mating eagles typically have 2 baby eagles called eaglets. When there are 2 eagles, they always feed the older eaglet until it has its fill, and then the younger eaglet. This results has an unequal chance of survival for the 2 eaglets. Suppose the older eaglet has a 50% chance of survival. So I'm just going to say older, survive, older, die, and it said 50%, so that's 50-50 so far. If the older eaglet survives, so this tail right here, the younger eaglet has a 10% chance of survival. So young survive is 10%. And then young die is going to be 90%. If the older does not survive, so now we are on this tail here, if it dies, then the younger has a 30% chance. So young survive, young die. What's the probability distribution? So what I'm going to do is I'm going to say, okay, let's think about it. If the old survives, I have 1 eagle. If the young survives, there's 1 eagle, so that would be a total of 2 eagles. The probability of that happening would be 0.5 times 0.1, which is going to be 0.05. If the older survives and the young die, I'd have 1 eagle, and the probability of that happening is 0.5 times 0.9, which is going to be 0.45. The probability of older dying, that'd be no eagle, and younger surviving would be 1 eagle, so I have 1 here, and that'd be 0.5 times 0.3, which is going to be 0.15. This one would be 0 and then 0, so this would be 0 eagles, and that would be 0.5 times 0.7, which is 0.35. These are disjoint, and if I add those all together, I'm going to get 1 total, because 100%. So I am able to put these 2 together, because they both represent 1 eagle living. And so that means I have a 5% chance for 2 living, which that's 5%. And that's 5%. I have a 50 or 60% chance of 1 living, so that's 60%. So obviously we know which one it is, and a 35% chance with none of them living. Again, expected value. So 1 times 0.2 plus 2 times 0.45 and so forth and so on. Suppose each ticket costs $12. Based on the distribution, what's the mean cost of the show? So you're going to do the same thing. 1 times 0.2 times 2 times 0.5, 1 times 0.2 plus 2 times 0.45 plus 3 times 0.1 plus 4 times 0.2 and 5 times 0.05. And that's 2.45. So that means that I have an average, an expected value, or a mean of 2.45 tickets purchased. And notice they have that right there, but that's not the right answer because it's asking 2.45 tickets times $12. And of course, then that's going to get your answer to $29.40, which is the actual answer. All right, I hope all this helped. And of course, remember, you can go through it. I have all the keys here in the back of the packet, and then the PDFs are online. All right, thank you so much. Questions, video 3. Okay, I am now on page 29. Okay, so test statistic. If you look at your formula chart, and actually in the calculator cheat sheet, you can see that this is going to be a 1 prop. And so with a 1 prop, I'm looking for, you can see this, and I need the P hat minus my P over square root of PQ over N. So you're going to be looking for this, and this is going to be the same. So when I go like this, I know that's not it. This, okay, that's 40/60, that could be it. This, well, that could be it if those are true. I haven't even looked to see which one's right. This one doesn't match there, so that's not it. This one doesn't match there, so that's not it. So I know it has to be either this one or this one. So obviously, if I read the question, I mean, this is without even reading the question, I could tell which one it is because it's a test statistic. And remember, you can look on your calculator and you can see what this formula is for the test statistic for a 1 prop z-test, or you can look at your formula charts. Now, if I read this, obviously this is going to be, it says a survey has a random sample of 1,045 adults and found that 60%, boom, 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 that's my P hat, is going to be, is going to, and so that's why I know it's going to be C, in fact, right here. All right, for this one here, so same idea. I'm just going to look here and check it out because remember just what I just said. I've got P hat minus P over square root of PQ over N. So remember, these two have to match. So I look here. Obviously, those don't match, so that's not it. These match, so that could be it. These don't match, so that's not it. These don't match, so that's not it. And these match. I don't see the rest of this one, so that could be it as well. So let's see what this is, and basically the only two that it could be is if, let's look at this, is this P hat or is this P hat? So reading it, it says according to the government data, 22% of children in the United States under this age of 6 live in the household according to incomes. So that, reading it, looks like P to me because it's P, remember, is the population, and P hat is my random sample. It's the sample. So if we keep reading it, and just to make sure, a simple random sample of 300 children in the United States. So that's 300 is my N, and it says, as I keep reading, which of the following was selected in the early childhood. If the government data are correct, which of the following best approximates the probability that at least 27% of the sample of children. So my P hat is in fact 0.27. So 0.27 would be P hat, which would be B, and P is going to be 0.22. Okay, for a z-score formula here. So I'm just looking at the z-scores, and let's see what we have, if it's means or if it's percentage, but it looks like it's going to be X bar, so it looks like we're going to be doing standard deviation with sigma. So let's go ahead and read it. Employees at a large company can earn monthly bonuses. The distribution of monthly bonuses earned by all employees last year has a mean of 2.3, so X bar of 2.3. and a standard deviation of 1.3. Let Z represent the standard deviation of a normal distribution. If X bar represents the mean number of monthly bonuses earned last year, a random sample of 40 employees, which of the calculation will give the probability that's less than 2. Okay, so 2 is going to be, so it looks like that I have, this is all employees, so really I marked this wrong. It shouldn't be X bar, it should be mu. So really, and then, and that should be my X bar, right? Because that's going to be my sample. What I'm really getting at is it's the same idea of the statistic minus parameter divided by the standard error. But the statistic is the X bar, that's the 2. The parameter is what I've known to be true, the mean, which is mu, which is 2.3. And then this is going to be my standard deviation of 1.3 divided by square root of 40. And again, this can be looked onto the calculator or it can be looked in the formula chart. The formula chart, of course, has it. And when I look through this, I see that this looks like it is. I'm just making sure nothing else is and I didn't miss a sign. Yes, that's correct. Okay, so it is A. In a large city, is 65% in favor of increasing taxes to support the public school and 35% against such increase. If a random sample of 500, what's the probability that more than 200 of the people will be against the taxes? So I need to see what's this probability here. All right, to be able to see what this probability is, it says more than 200. Well, let's just do this the way we would do this with, this is going to be, if it's a z-score, observed minus mean divided by standard deviation. So that's just going to be the z-score is, it says 200 of the 500, 200 of the 500, minus, what was it, the percent that it says, 35%, divided by the standard deviation, which is going to be this, of course, 0.35, 0.65 over 500. So that indeed is E, what it's measuring. Let's talk about why it's not A and why it's not B. These are binomial. This would sound like what's the probability that 200 of the 500 people in any room believe 65% versus 30% using the against or for, and this would be the opposite of that. But this would be, given that there's 500, what's the probability that 200, any 200 are there? But this one here is specifically against here. This is just some sort of combination where I'm asking for all the different combinations of the 200 people. This is just asking for the exact probability. All right, you have to know how to make sure you know how to do the expected value. And remember, to do that, if I'm acting for the expected value or the mean, remember it's 1 times 0, this times this one, plus this one times this one, plus this one times this one, plus this one times this one. This one asks, so that's how you do expected value. Let's see what this says. The faces of a 4-sided fair dice are numbered 1 through 4. For a certain game, just erase this. For a certain game, the die is tossed and the number lands face down as recorded. The table below summarizes the points for someone that earns the number of points. So if they roll a 1, they get no points. They roll a 2, they get 1 point. Roll a 3, no points. And roll a 4, they get 2 points. Consider 2 independent tosses. So they're doing this 2 times. Let the random variable S represents the sum of the points earned from the 2 tosses. What's the probability of the distribution S? Well, obviously we know the probability of all of these is 1/4, 1/4, 1/4 originally, correct? But now let's say what happens if I roll it twice. So if I roll it twice, this is how you could kind of do this. Is I do 1, 2, 3, 4, 1, 2, 3, 4. And if I roll a 1 and then a 1, that would be 0 plus 0. If I roll a 1 and a 2, because I'm just doing the 0 plus 0 there. If I roll a 1, I get a 0. If I roll a 2, I get a 1, so that's 1 point. So this one's just, if I roll a 1, that's a 0, obviously, and a 3, that's a 0, and then a 1, that's a 0, and a 4, that's a 2. So if I roll a 1 and a 2, that's a 1. If I roll a 2 and a 2, that'd be 1 plus 1 is 2. If I roll a 2 and a 3 is 1 and 0. A 2 and a 4 is 1 and 2 is 3. Then I would keep going and I'd say, okay, a 1 and a 3. A 1 and a 3 is 0. A 3 and a 2 is 1. A 3 and a 3 is 0. And then a 3 and a 4 is 2. A 4 and a 1 is 2. A 4 and a 2 is 2 plus 1 is 3. A 4 and a 3 is 2. And finally, a 4 and a 4 is 2 plus 2 is 4. So now I would say, okay, so I have 4 zeros. And so in order to be able to zero, I have 1, 2, 3, 4 times 1, 2, 3, 4 possibilities. So that's 16, possibilities. So a 4 out of 16, or 1/4, obviously, 0.25. If I were to put it in decimals, because that's what it looks like it is. A 1, the probability of getting a 1 is going to be 1, 2, 3, 4. So a probability of getting a 1 is also 0.25. The probability of getting a 2 is going to be 1, 2, 3, 4, 5. So 5 out of 16. The probability of getting a 3 is going to be 1, 2 out of 16, or 1/8. And the probability of getting a 4, obviously, is the 1 out of 16. So when you go ahead and do the math, you can see that D is the only one that works, 0.25, 0.25, 5 out of 16 is 0.3215, 2 out of 16 is 1/8, or 0.125, and 1 out of 16 is 0.0625. So that's how you would do that problem. Expected value, again, as I said, you're going to multiply these. And then that's going to get your expected value. And that tells you the number of sweatshirts you're going to buy. And then each sweatshirt sells for $25. So what's the total expected value of the sweatshirts? So you'll take the expected value, and then you're going to multiply it by $25. So you're going to put this into your calculator. So let's go ahead and put it into our calculator. Let's get my CAS here. And you have 0 times 0.3, which is 0, so I'm going to leave that. 1 times 0.2 plus 2 times 0.3 plus 3 times 0.1 plus 4 times 0.08 plus 5 times 0.02. And that's my expected value, so that's 1.52. And then I'm going to multiply it by $25, so because that's telling me I'm expecting to get 1.52 t-shirts. $25 is $38, and that's where I get $38 from. All right, this is mating eagles typically have 2 baby eagles called eaglets. When there are 2 eagles, they always feed the older eaglet until it has its fill, and then the younger eaglet. This results has an unequal chance of survival for the 2 eaglets. Suppose the older eaglet has a 50% chance of survival. So I'm just going to say older, survive, older, die, and it said 50%, so that's 50-50 so far. If the older eaglet survives, so this tail right here, the younger eaglet has a 10% chance of survival. So young survive is 10%. And then young die is going to be 90%. If the older does not survive, so now we are on this tail here, if it dies, then the younger has a 30% chance. So young survive, young die. What's the probability distribution? So what I'm going to do is I'm going to say, okay, let's think about it. If the old survives, I have 1 eagle. If the young survives, there's 1 eagle, so that would be a total of 2 eagles. The probability of that happening would be 0.5 times 0.1, which is going to be 0.05. If the older survives and the young die, I'd have 1 eagle, and the probability of that happening is 0.5 times 0.9, which is going to be 0.45. The probability of older dying, that'd be no eagle, and younger surviving would be 1 eagle, so I have 1 here, and that'd be 0.5 times 0.3, which is going to be 0.15. This one would be 0 and then 0, so this would be 0 eagles, and that would be 0.5 times 0.7, which is 0.35. These are disjoint, and if I add those all together, I'm going to get 1 total, because 100%. So I am able to put these two together because they both represent 1 eagle living. And so that means I have a 5% chance for 2 living, which that's 5%, and that's 5%. I have a 50 or 60% chance of 1 living, so that's 60%. So obviously we know which one it is, and a 35% chance with none of them living. Again, expected value. So 1 times 0.2 plus 2 times 0.45, and so forth and so on. Suppose each ticket costs $12 based on the distribution. What's the mean cost of the show? So you're going to do the same thing. 1 times 0.2 times 2 times 0.45, 1 times 0.2 plus 2 times 0.45 plus 3 times 0.1 plus 4 times 0.2 and 5 times 0.05. And that's 2.45. So that means that I have an average, an expected value, or a mean of 2.45 tickets purchased. And notice they have that right there, but that's not the right answer because it's asking 2.45 tickets times $12. And of course, then that's going to get your answer to $29.40, which is the actual answer. All right, I hope all this helped. And of course, remember, you can go through it. I have all the keys here in the back of the packet, and then the PDFs are online. All right, thank you so much.